So, hello, welcome everybody. Good to see you all here. Very strange to see you in person. It is also a little strange for me to stand here and have the camera there and not be the other way around and all these sorts of things. But of course, the important thing is that we get to be in the same room and interact in person. First of all, there's a little list that's going around, but while this list is going around, let me just quickly do some introductions here. So I'm Sándor Fekete, this is Online Algorithms, and I'll tell you a bit more about what is up, what we are expecting. There's one more person here. Please introduce yourself.
Yeah, I'm Michael. I'm just recently started working at the Algorithms Institute, and I will be lecturing the tutorials mainly and giving you the homework. So maybe we will see how it goes this semester. So the first tutorial will be next week on Monday. So I will see you guys hopefully there. And the tutorials will also be recorded, same as the lecture, and uploaded afterwards. But I encourage you to come to the tutorials to ask questions and stuff like this.
And we should also do more introductions, but let me start out of order with one person here, and that's Peter.
Hi.
Maybe you can say a few words about yourself and all this.
Yeah, I'm currently doing my master's here, and I'll be helping out with the tutorials as well. I think my exact role is to be shown, but yeah, nice to meet you everyone.
Okay. Now, the luxury we have is that we can interact. And of course, that will help to know a bit more about who's around here. So we can do, that's time well spent, quick introductions, say who you are, what you study, what your semester is, why you took this course, what you're looking forward to.
My name is Gaston. I'm a master in informatics. This course I'm interested in because last semester I just did the computational theory with you. And algorithms, I'm very interested in algorithms and to learn about them. How can we deal with it and go with it?
Excellent. Welcome. Let's go like this.
Okay, hi, I'm Jan. I'm 28 years old. I'm studying in the master degree business computer science. I heard CG last semester, and now I'm here with online algorithms. For me personally, a little more interesting because I'm going to be a trainer and very interested in something like SEO, which is based on algorithms. So yeah.
Okay, good to have you here.
Yeah, I'm Daiko. I'm studying data science, and so I've already attended some algorithm classes and find them pretty interesting. So I will see how this one is going.
Okay, very good.
I'm Svenja. I study computer science in master degree, and I'm here because I don't know. It sounds interesting. Yes.
Okay.
I'm Tom. I'm also studying computer science in a master degree. Last semester I took CG and MMA, and that kind of got me hooked on algorithms. And so I thought, okay, maybe check out this lecture as well.
Hi, I'm Nick. I've taken pretty much all master algorithm lectures so far, and they were all fun. So I'm looking forward to this one as well.
Do you remember who this is? This is Peter.
Hello, my name is Nico. I'm a master here in studying computer science, and I also listened to CG last semester and also MMA. And yeah, we're just going along the road, some lectures in the IVR. So looking forward to all of them.
My name is Boris.
Good that you remember that.
It took me a while. And I'm studying computer science, I think.
And yeah, that semester I took a CG as well. And I think algorithms is an interesting topic in general. And so yeah, I might find this lecture interesting.
We'll do our best.
I'm Philip. I'm in Master of Computer Science. I'm 24 years old. And yeah, recently I've been a little interested in web crawling. And I thought maybe that could fit to that topic in this lecture.
We'll see. Online. I'll talk about what kind of online we look at.
Hello, my name is Jan. I'm studying my master's degree in computer science. Actually, I'm going into a different field, but this course seems interesting to me, so I'm here.
I'm Hendrik. I'm studying computer science, my master's degree, and I'm interested in algorithms in general, and found this course quite interesting.
My name is Nils. I'm also doing my master's degree in computer science. I took a lot of algorithm lectures in the past during my bachelor's, and yeah, I enjoyed them very much. So I thought, yeah, why not continue there and so on.
Yeah, I'm Tobias. I'm in the Masters of Business Information Systems, and I did a lot of algorithm stuff in Bachelor as well, and I wanted to continue.
My name is Patrick. I'm also a master in my first semester, and I'm interested in algorithms in general, so yeah.
My name is Matthias. I'm studying Master of Computer Science, and I do not hear a lot yet about online algorithms, so I want to learn more about it.
Excellent.
Hi, I'm David. I'm at the end of my bachelor's in computer science, and I'm looking forward to my master's, and I'm using my knowledge of algorithm theory.
I'm Dennis, and I'm studying computer science on a bachelor's degree, and I was reading about bachelor's. The topic seems quite interesting, so I thought I'd give it a shot.
Hello, Florian. I'm a bachelor student in IST, and I probably took almost all of the algorithm engineering and courses.
And we're not counting how often?
This one, second time.
Okay.
So that's why I'm again here, because online I didn't took the exam.
We'll do some variations.
Hi, I'm Jakob. I'm my master's degree in computer science, and yeah, I also took some algorithm courses in science. Hi, I'm Jonathan. I'm also studying computer science master's degree, and yeah, I was also last semester I took MMA, and I want to see what the algorithm department is about.
Hi, my name is Vasim, and I'm studying Master of Data Science. I studied a lot about algorithms in my bachelor, but to be honest, I have no idea about online algorithms, so I hope this lecture will be good for me.
Welcome. Michael, kannst du mal schauen, ob das vom Ausschnitt her ist okay ist oder ob er sich da ins Bild gesetzt hat? So, welcome you all. You've already been communicating with me, and you will continue to communicate with me, even if you don't say much. We can interact and communicate visually, but I would strongly encourage you to also speak up and talk and discuss with me.
So, see you guys next week, and see you later. Thank you. Bye.
So the luxury we have now, and I think we got to appreciate this a bit more, is we can do more interaction. And that's a main feature of when you do science, when you do computer science, and when you do algorithms. It is not something that you just learn and memorize, and the human brain isn't built by like you just copy an image of the lecture notes into your brain and then you have it, or you just implement the algorithm into your brain and then you run it. That's what we have computers for. But what humans are good at is very different. Humans don't have read-only memory. Humans have it's always read and write, and it's a lot more. It's about connections and using things to enhance them, to improve them. And the other thing is, when you are looking at a topic like algorithms and computer science in general, it doesn't end. It's not that I say, this is what you should look at, and I'll bring you a couple of books next time. I'll show you the books. I deliberately didn't do that today. It's like, this is that book, this is that. We'll talk about that in the future. Because the point is, and the point is of computer science or data science, it's not so much about having specific knowledge. It is more about a way of thinking. It is more about solving problems, thinking about problems. And that is what makes you good and professional at what you're doing and what you will be doing, because it doesn't end. And that's the nice thing. When you have something like computers and computer science, things change and things will continue to change. Even when you have your master's degree, a few years down the road, there will be other problems, there will be other methods, there will be other machines and other situations that are difficult, that need to be solved. And that is where we need professional masters, computer science, data science, not because they know everything, but because they're able to handle situations and questions that nobody knows yet really how to do. And that's a key part of this class as well. So I will show you, I will introduce you to some questions, topics, concepts, results. But this is not aiming for giving you, this is everything you need to know about online algorithms. It is more about introducing you to a way of thinking, to a way of solving problems, to a way of discussing problems, and of course, in the process, also a number of results. But some of these results could be replaced by others, and it would serve the same purpose. In general, over the semester, you will notice that there's roughly a separation into two parts. And the first part, this is a bit like, quite a few of you mentioned computational geometry from last semester. The first part, just like that, will be basic concepts, will be textbook material, will be simple things that are so basic that you shouldn't miss them. Then in the second part, just like in computational geometry last semester, we will switch gears a bit. We will go from textbook basic things to more advanced research-oriented topics, which can be replaced by other research topics, but which serve to show you then that the basic things, which are in textbooks, continue and you can do something with them. So the second part, not necessarily 50%, it depends a bit like on our interaction as well. But the second part will be more recent research results, papers, and so on, which of course will also give you an idea to experience what it is like to think about these problems, ongoing, open research problems, and so on. So that second part will also be a number of own research results, not because I think those are the most important to know, but those are ones where I can tell you some stories and where I can show you how some of these things happened. There's obviously plenty of other things from other people as well. And that will include some things from the last few years, but we can talk and interact and so on. Now, that said, I should tell you about what is online algorithms. What does online mean? So online, we've been interacting online in the last 4 semesters, and of course we continue to do so by all these main means of communication. And let me mention that, of course, most of you have been to algorithms classes before. We can communicate online as well because you can send me email. There's a mailing list. If you haven't signed up to the mailing list yet, do so. I haven't kept track of exactly how many. This is 22 people here, but you can follow that. Also, of course, online, there's the video camera running. So, and the sound should be okay here. So you will get a chance to look it up afterwards. So if you don't understand some words that I'm saying because it's English or because it's an unusual term or because you just wanted to look it up again, you will have a chance to look this up again afterwards. So we'll make these videos accessible to you. Interaction online and so on. So don't be shy about sending email. If you have a question or problem, that usually works pretty well. You will probably get some answers soon. And if there's a question like a technical one about assignment problem or something like that, then we will give this back to you pretty fast. We have, as you remember from CG, for instance, which many of you noticed, mentioned, we have these quizzes. We'll bring in some quizzes as well. Not today, of course, but we'll get to that. Yeah, technical questions before I dive into the meaning of online. Exam. Yeah, that's the usual question. There will be an exam at the end of the semester. The default, depending on the number, is usually an oral exam. Whether that oral exam is going to be in person or online, we'll see how the world and the pandemic and all these things develop. But some kind of oral is the default. Now, if we get like 20 more people next week and so on, then at some point we'll look at that whether it scales. But yeah.
Does the oral exam have to be on English, or can we decide which language we choose?
Mostly these exams are in German, but it's your choice. I mean, German is fine, absolutely fine. If you want to do it in English, you're perfectly happy. If you want yet another language, we'd have to negotiate what it is like. So, but yeah, not C++. Okay. Yeah.
Would there be exercises or homeworks?
Yes. We will be doing some exercises, some homeworks. Now, this is something. It shouldn't be. I mean, it should be an opportunity, it should be training, it should be encouragement, it should be feedback. And we usually, that's our classical default from the past as well. We say like 50% of the assignment problems and so on and so on. But of course, in the last few semesters, we have played with this a little bit because this online format and so on made these things a little different. And in the last couple of semesters, we've tried out a few other things. Now, Peter is behind you and Michael is there. We've been talking about some formats and some ideas. So there are a few ideas of doing this. The key point is just following and listening and trying to understand passively is not the same learning experience and learning practice as thinking about some of these things, trying to solve it, and then maybe the joy of actually solving it, or maybe a few things that you understand from this context. That's the main purpose. So in the Prüfungsordnung, so in the rule book, there are some things about for this module that you're supposed to do some homework problems and then the final exam. But we'll see how this goes, right? For instance, with the quizzes in the last 4 semesters, we put in more quizzes to make sure that there's feedback, and we didn't put grades on the quizzes and so on. We'll talk about good formats and how these go. So by all means, if you experience that in the next few weeks, and if you say like, no, this was really helpful, let us know. If you say like, I'm not getting much out of that, or I would like to have something, like I'm missing some things here, talk to us. That's why Michael and Peter are there as well, so you have multiple people to talk to. And the main target is not this, or this, or this, or me, or so on. The main target are your brains. And those are the ones where the action should happen. And that's where my job is to make you use your brain, to make you think and work and understand, solve problems, and so on. Other questions? Not right now?
Are there big and small tutorials both on Monday or?
Peter, do you want to address that? Not yet. Not yet. We will. There will be a large tutorial, a major tutorial with Michael, and he mentioned that it will start next week, and we'll take it from there. So there will be some plan about what the schedule is and all that. But like I said, we have the basic plan, the default plan is there's a lecture every week, there's tutorials taking turns every other week. And, but we have talked about a few things that we will try out. Now, trying out means that we're trying things and see how they work and if they work. And if they work well, we will try to keep them and maybe even improve them a little bit. And if they don't work, we will change them. And of course, to judge whether they work, that is something that you should tell us. And also if you're getting what you need. Of course, like I said, we will do some discussion and interaction, and from that we will, of course, get a feeling for where things are. Okay, so far so good. Has everybody had this list? Thank you. I have 22 names, that is perfect. Now, if you don't mind, I would take a photograph. I will not post this, but it will give me a chance to at least match the upper half of your faces to the names, okay? Wide angle. Excellent, thank you. Great. Okay, that it gets us to this. So online, of course, like many words, for instance, this word programming. Today we think of programming as typing code into a computer. Back 60, 70 years ago, people were thinking of programming as a different thing. It meant systematically doing something, not necessarily doing it, having a computer do it. And of course, online, now of course everybody is online all the time. This phone is online, and you're online, and some other people are online. But what does really online mean? It's not necessarily per se electronic. You can also think of this as ongoing. There's something that still continues. And the idea of an online algorithm is something that works while there's still other activity going on. So an algorithm that works while it still gets input. And when you think about that, that is a very normal situation, right? I mean, yeah, we're making decisions. We as humans are making decisions in situations that are still ongoing, that are still changing. And That is sort of a normal thing. So a classical offline algorithm that gets its data, its input, and then produces the output. So it's strictly separated here. And then, of course, in an online world where things are changing, where things are happening, that is not necessarily so well separated. And let me illustrate this by a very, very simple, basic example. What's an offline example for tour planning? Well, the traveling salesman problem. What's the input for a traveling salesman problem? You may have a graph with edge weights That's your input. A shortest round trip. Now, I could now go on to specify and define what a round trip is. I think you know what a round trip is. We want a permutation to go through all these vertices. And shortest is, of course, that you minimize the total edge weight. So start at some point, visit all of these vertices, and return to the origin. You've all heard this, and we know it's hard, right? It's hard. Why is that problem difficult? What makes that problem difficult? It's the fact that there's a large number of potential solutions. If you have n vertices, then there may be n factorial different permutation, n factorial different tours. And finding the best one may take a while. And we know there's a formal way of describing and proving that this problem is hard. This is NP complete. Right, so even with this full information, that is a difficult problem. That is a provably hard problem. That is known to be, in a specific way, one of the hardest problems in optimization that we have. But there's a totally different source for hardness, for complexity, for difficulty. And that is not having the full information. That problem is difficult even if you have full information. But of course, it may get difficult in a different way if you do not have the full information. For instance, if you are running a tow truck service, and you need to efficiently service all these broken down vehicles. The offline version is somewhat similar. Like you could have all these locations where these cars are that need help and that need repair, and you want to find an optimal tour to get there. But of course, the nature of tow trucking is that people don't plan to have an accident. People don't plan to have an engine failure. People don't plan to have a flat tire. So it's not known in advance. Here, you could take this, and if you think of, for instance, a shipping service, one of the ones we've been using over the last few years and all that, you can just plan an optimal tour here, take the data and all that. But here, you don't know where you want to be, where you need to be when you start your day. Time plays a role. While the day goes on, you may be heading there because that's where a car has broken down, and as you're leaving from there, just where you were before, a moment before, another car breaks down. So you can spend a lot of time. And if you just had waited a moment longer, you could have taken care of this thing and then gone over there and fixed that. And you can imagine that problems of this type happen all the time. And of course, the more we have computers which are portable, which are everywhere, which help with decisions, the more scenarios we encounter where the computing device that carries out some computation and the setting where things are changing, where decisions have to be made, where activities are happening, they're not separated. So it's not that you say at the end of the day, I'll wait and look, where have all the cars broken down, and then I'll do it on the next day. You can do that, but that's obviously not so pleasant for the people. So even if you have just two locations, and you have your tow truck and you go back and forth between those two locations, that already is not so clear what you should be doing. Because even though this is not a difficult problem, should I go, if I have three here, say three locations, should I go here or should I go here? Or should I stay or should I go? If I give you the sequence of events in real time, that is not so difficult for just something like this. But if I don't tell you ahead of time, and that's the nature of real life events, then you have to make some decisions and you have to come up with some strategies. There are a whole number of questions that follow from this. Many are, in the beginning, are relatively easy, and I'll show you a very, very simple one, which is even simpler than going back and forth. There are some basic questions in the beginning, like what kind of decisions, how do I make these decisions, and what's a measure for the quality of a decision? Is that a good decision or is that a bad decision? How do I compare different strategies? And so one basic one is like, what information do I have? How can we make decision? How do we compare the quality of decisions? And that's, of course, really, really very general. And that, of course, depends a bit on the context. And that, of course, in some cases will be subject to discussion and debate. So, let me start with a simple example, a simple scenario. And it's summer, spring, it still feels very cold, so well, you know. But when you think back, the last kind of news that we had before this whole pandemic started, I remember this was like February, March 2020. And there were some things going on in Austria, right? And there was Italy, there was Austria, there was something in a ski resort. So let's think back and let's put ourselves into the mind of skiing. Okay, skiing. This example is called the ski rental problem. And you're on vacation. You went skiing in the Alps. You want to go skiing, that's what you're here there for. Of course, there's après-ski, but you do that after the skiing, as the name indicates. Now, of course, you need equipment. Equipment means you need skis. And you have two choices to get skis. One is you buy a pair of skis. And of course, bringing these skis along from northern Germany doesn't really make a lot of sense. You have, of course, it's in the Alps. There are shops, there's nice things, you can try them out, you can check and get good recommendation. Maybe your coach give you some hints like what you should be doing. So you could buy a nice set of skis. And you can buy a pair of skis for, let's say, 200 euros. That's an okay price. I mean, they're not super fancy, but they're already pretty decent enough that you can use them for a while. The second is you can rent skis. Rent skis. Rent them for 20 euro for the day. 20. Then you have them for the day, you use them, and then you hand them back. And the next day, same question. Okay, do you go skiing or not? So far, so good. I mean, when should you buy them? When should you rent them? Makes sense, right? So, yeah.
When you use them 10 or more times.
When you use them 10 or more times, right. There's no resale value and so on and so on. So if you're going to be there for at least 10 days, you should just buy them. But here's the catch. As you know, skiing is a little risky. So something could happen. You could fall and break a leg, or you could also catch corona and then be out commissioned for that. But the nasty thing is you don't know ahead of time how many days you will be skiing. So if you buy them on the first day and you say, I'm going to be here for 2 weeks, that's 280 euros in rental, that's cheaper. But it could happen that during the first day you break a leg or you fall or whatever. The weather is nasty, let's keep it easy. The weather turns out to be horrible and you will not be able to ski anymore. Then if you then spend 200 euros on buying skis and you only need them for this one day, that's a bad deal. And that's the unknown piece of information. So the unknown piece of information is very, very simple. On what day will you stop skiing? So that choice is per day. On what day do you buy? Now, there's something to be said, of course. You could look at this and say, like, of course I know. Like, after the first day, I know that skiing is the thing for me, and I love skiing, and I will go skiing forever and ever. But it's not your choice. Something could happen. So it's a mathematical scenario. So you don't know ahead of time what the last day of skiing is like, when it is, what the number is. That's a number B, and that's a number, let's call it L for last. Now, a few comments about this kind of thing. What information do we have? Well, we have the information about the cost. We have the decision to do this. And, well, there's some information we do not have. That's the information about this. So that's a number we pick, and that's a number that happens to us. Now, number that happens to us is, of course, when you look at these things, there are different ways to look at these things and analyze them. And one thing that is standard in this context is the worst case. The worst case, or the pessimistic view, or the maximum regret. There will be a few situations when we're talking about expected values and probability and so on. We'll get to that when the time is right. But let's look at the worst case. So, the worst case. What is the worst case when you make a decision? What is the worst case? So yeah?
The
worst case would be buying right after I can't go skiing anymore.
After you, well, or...
After. If I don't go skiing at all anymore after I bought them because,
right.
for example, an accident happened on my way back from the
right. Let's keep the order right. So you buy. Now, if you say, I know that I will not be able to ski anymore, and then you buy, that is not the worst case, that's the dumbest case, of course, right? So the worst case is you make that decision, and that's the last day you ski.
N equals D plus 1. N equals D plus 1.
Yeah. So, or the last day is L equals B.
Yeah.
Right? Let's keep this in mind. I mean, we're thinking this is not about formal definitions so far. Mostly, it is more about looking at this. Now, this about the worst case. Here, it's relatively clear what the worst case is, right? You spend this maximum amount of money, you will never ever have to pay anything for the skis again because you bought them, they're yours, you don't need to rent, and then you don't get any use. That's sort of obviously the worst thing that can happen. We will be looking at other situations, at more complicated problems, of course, where it is not quite as clear what the worst case is because there's a more complex situation where we need to make more complex decisions, and what the worst case is not completely clear. There's a whole sequence of possible events that happens. But what often happens, what often helps, is to think of the worst case as an adversary, as an enemy, an opponent, as the devil. Because here we can identify this. And when somebody makes a decision and you try to make that decision as bad as possible, then you think like, okay, how can I make this person look bad or feel bad? This is a fundamental thing in online algorithms because when the decision is made, the future is not known. The full input is not known. So out of all the many possible choices of L, we could have L. I mean, L needs to be at least B because then if skiing, like I said, the dumbest choice is you buy your skis after you know that you will not ski anymore. So that this is at least B is clear. Now, of course, you could have L bigger and bigger and bigger. And so intuitively, it doesn't make sense. We need to analyze this. What's a good comparison for the quality of solutions? We'll look at that. This concept that we'll encounter repeatedly is, we think of the worst case as a personification, an adversary. Not because we believe in evil incarnate, the devil, something like this, but because often it is not so difficult to deliberately choose the worst possible option. The worst case, and you say, what is the worst case? Well, that is clearly the worst case. And so you optimize over something. Now, that is thinking of an adversary. If you were playing fate, if you could make a decision on what happens in the future, what would you choose to make this algorithm look really bad? Clear in this case. Okay. Let's look at the quality. How can we compare the quality of decisions? So, of course, you could look at the amount of money you spend. That's one thing. But you can also look at how much money you spend compared to how much you would have to spend. What you would have to spend if you knew the future. So I remember one of the first talks I ever attended on online algorithms that had the title, "How much is it worth to know the future?" And for those of you who are in business informatics, that's a fundamental question. How much is it worth to know the future? How close can you get to an optimal solution with full information without having the full information? And now, when you compare these two things, like in many, many situations in algorithms or in science in general, you look at these two values and you can look at a number of different things. You can look at the difference, or you could also look at the ratio. What's a good measure here? Well, one of the two is obviously a good choice, right? Difference versus the ratio. Do you have a preference? No? Any favorites? What should we try to minimize? The difference, the ratio? Are there good reasons for one or the other? Yep.
Wouldn't that be dependent on essentially what we expect, how much time we would be spending skiing? I mean, if we have an expected time of just being there for 15 days, for example, then the difference may be better. But if we want to be there for 15 days instead of 15, then maybe the ratio would make more sense. I guess if it's the value of days was higher, we would prefer the ratio over the...
Now, as you know, there's this thing called inflation. We're just getting to know it again after many years without inflation. And that means the value of money changes. I gave you this scenario with 20 euros per day for rental and 200 euros per day in rental. Now just imagine we have a few more years of serious inflation and the whole thing changes to 2,000 for buying a pair of skis and renting for 200 euros per day. What does that change? Does that change the difference? Yes, it does. Does it change the ratio? No. If I had given you another example where buying is 20 and renting is 2, so these 20 and 200 are basically scale factors. So would you use a different strategies if you were in a 200 versus 2000 setting? Would you use a different strategy if you were a 2 versus 20 strategy? Probably not. So the basic strategy in this case here is independent of whether this or that. Now you could argue back, and rightly so, saying, well, you know, the difference still, I still want to minimize the difference and all that. Fair enough. But what is good fair comparison for the difference, and then I could probably argue back and say, yeah, but like, okay, you want to minimize the difference, we agree on that, but you should normalize that difference and divide it by a scale factor, and then you are looking at the ratio again. So not giving a final answer to this, I'm just trying to sort of make you think about what a good measure is. So let's settle on the ratio. And the measure. When I write this down, then I have such a ratio. That is something that actually is also considered in other contexts of algorithms. For example, preserve that here. When you look at the traveling salesman problem, finding an optimal solution can be really, really hard. If I give you 100,000 different cities to visit, finding an optimal tour may be difficult. But if you are able to find a good solution, maybe one that is only 50% more expensive than an optimal one, then you're looking at the ratio between what you can get and what an optimum would be. That is, in classical offline algorithms, that is known as an approximation factor. So that's known for offline algorithms for hard problems. The reason why these are considered that's hard to compute. And there's a whole class, last summer I taught that's called approximation algorithms. And next year maybe, who knows, I'll be teaching that again or whatever. There's a reason that there's a lot of solutions, but finding the right one is difficult, but maybe we can find one which is good compared to that. And here, there's another term that looks at the same concept. It's called the competitive factor. So, how well can you compete with a situation if you knew the future and could just compute the best solution? That's the competitive factor. And you see, there's a good reason for that as well with the analogy here. Now, of course, if opt is 0, that's not a really good measure, but for most purposes, we don't get a 0. I mean, even if you just rented once, that's 20 euros, and that's a positive number. And for most problems we are looking at a positive value, so there's no 0 in the denominator. There can be situations where knowing the right things can get you something which is really, really very, very cheap compared to what you do if you don't know what's coming. And then this can get really, really big. Now let's look at our ski rental problem here. How well can you choose the day where you buy your skis? So if you buy on the first day, what is your competitive ratio? What do we pay? That was B. Right. And what is optimal if you buy on the first day?
20 range at once.
So what's our competitive ratio if we buy on the first day? 10, sure. Competitive. And that is nothing else than B divided by L. What's the other extreme? The other extreme is if we never buy. If we never buy, how much are we going to pay then? Zero. No, you're going to rent on the first day, you're going to rent on the second day. You're going to spend, you'll be skiing on forever on rented skis. Okay? Now, I mean, that's not realistic in the climate change and all that. Eventually, there's not going to be any snow left, but this is a mathematical question. So, yeah.
L times 20 euro. L times 20 euro. Where L is the number of days we ski.
Yeah, so if you never buy and if you keep skiing, like what's the competitive ratio here? Is that a number? No, so what do you say?
No future. It depends on the trend. How long?
Yeah, I mean, this is unbounded. Infinity, whatever you prefer. Right? You can spend an unlimited amount on rental. For every number, there is like sufficiently many days. You take 1,000 days, you pay 20,000, and you could have bought. That's 20,000 divided by 20. That's 1,000. But if 1,000 is not enough, then you just, right? So that's unbounded. Now there's some finer points if you say like, well, infinity is not a number that I accept, but I can say like, you cannot put a bound on it. It can be as much as you want. So, somewhere between 10 and infinity, what happens if you only buy on the second day? What is your competitive ratio then? Let's draw that. So this is not a super difficult problem. This is not a super difficult question. What is important is to think about how this plays out, because it gets you into the right frame of mind for more difficult problems. So, B. Let's call this C. So if we put in a 1, we see we get a 10. What do you got here? Yep.
I'm not sure if I'm on the right track, but when we use the optimum of 2 days, like renting for 40 euros and we break our leg on the evening on the second day, that's like the optimum. We just rent for 2 days.
Okay.
And if we buy it
on the second day,
we rented it on the first and bought it on the second, so we have 220 euros. So
we have
220.
220, yes.
Yeah. So the optimum, the ratio is 220 divided by 4.
Right. 1, 2, 3, 4, 5. Okay. $240 divided by 60. So we keep getting better, right? We know eventually we're going to go to infinity. So some point somewhere here, this is not going to get, we're not going to get negative. We're not going to go below 1. So there will be a minimum here. Shall we keep going? No? You don't want to keep going? Okay, we stop. Let's keep going. What do we get if we have 4? Yeah, Peter. I thought you were you were just wiggling your hands. Okay, then.
I think it's going down to 2.
You think it's going down to 2?
Yeah.
You're thinking ahead. Okay, that's fine. Question is, can you get below 2?
3.25.
In this case, let's keep it plain and simple. We got here 260 divided by 80, and that is indeed 3 1/4. 1, 2, 3. Hey, that's easy. And you think we're going down to 2. Well, that's a good feeling. But that's just a feeling so far?
Well, the 10th day it's 408 and 200 optimum. And
On the 10th day, okay.
I think then the optimum doesn't change anymore. So it stays at 200 because we just buy it.
So let's go here. What do we pay on the 10th day?
We pay 400 because we rented for 9 days. Yeah,
Right.
So
380?
380 divided by 200.
Divided by
200.
200.
And skip the thing.
And we're looking at 1.9. Hey. Better than 2. What happens on day number 11? Let's just try that.
The optimum stays at 200.
Mhm.
We would have just bought this fee and paid. The paid amount increased.
10 days rented, 1 day, 1 then bought.
Yeah. Divided by 200, so it stays.
And of course you realize that this is going to stay. So going further makes things worse. That's the best. We can check, we could check these things in between. But there you have 360 divided by 180. What is that? That's another 2. Surprised? We can beat the 2. Is that a proof? Not exactly, but yes.
Yeah, we could now prove that we could check all the values in front of 10, and we could prove that the values after 10 only increase.
Right. So the values after 10 only increase because the denominator stays the same and the numerator goes up. So it is going up. Right? What is 1.9? Why 1.9? Why not 1.5 or 1.99? Why not 2? Tobias, do you have a suspicion?
I think it's B minus L over L. Something like that. B minus L over L. Something like that.
B minus L over L. That's a guess.
No, it's not exactly right, but I think this has something to do with B and L.
Yeah. So how about
Sounds good.
Sounds good? That works, right? Why is that, in fact, what's happening here? If we replace the 20 and the 200 by this, what are we paying here, generally speaking? What are we paying here? There's something happening here when the total rent that we're paying oh no, L. Yeah. Yeah, I think that's good. I'm mixing up the parameters a little bit. B was the buying and like the day. So I'm sorry for mixing up the B and the L. I think we stick it with that, okay? I mean, I'm using B for the cost of buying and L for the cost of renting, not the last day. So on this blackboard, I switched notation when you compared to before. Okay. So what is this 1.9 and what is this 200? This 200, yes?
The 200 is L and the
Is
B ratio.
B for buying.
Oh yeah, B. No, L, right? L was the one, no it wasn't. Well, it was a little bit confusing because when you introduced the days, I think L was the longer time.
Yeah. I'm sorry. How about I make this right? That's what happens when I make this right. That's a big B for buying. And that's a small b for paying a small amount. No, that's stupid. That is stupid. Sorry. That's a small r for renting. So.
Okay, so the denominator is B and the numerator is big B times 2 minus r.
What is this? And what is that? That here is a B. Yes?
B plus, and do we use the for notation small b minus 1 times r. L minus 1 times r. The last day.
Yeah.
Minus 1.
Now what is the last day? I mean, that's the thing that is moving here. So let's call this so that's that whole sequence. Here and before.
But why L times R and not L minus 1 times R? Because on the 10th.
Okay, fair enough. Yes, let's do it that way. Yes, thank you. That's what's happening here. What do we have before? What are we paying here? Yep.
B, or the numerator is the same, B plus L minus 1 times R. And
here.
The numerator is just L times R.
I think we should mark this, right? This is the optimum until when? Yes?
The L times R equals B.
That is here. Okay? So far, I mean, that's just a mathematical distinction when whether this is better or that is better. And this whole thing is describing okay? So, it's not a super difficult problem, but this analyzing this case distinction gets us into more abstract territory. Okay, so we see that's always what we are paying. Strategy L. Y on day L. Cost, as we set up there, B plus L minus 1 times R. Okay? Now, those are all the strategies that they are, because we make a single decision and we make that on del L. So that's the full zoo, the full family of strategies. So, what's the competitive ratio we're getting? We have it there, so we can just write it down. L then we're getting B plus LR minus L divided by LR. Then we have B plus, well, no, this is not right. I'm sorry. This is an R. My mistake. Right? Okay.
The lower line is R as well, right? In the second case,
Yes.
R minus R.
Yes. Sure. Thank you. I fixed the mistake and made it again. So, what do we get if we choose that case here, LR equals B? Yeah.
And the terms B divided by LR or LR divided by B are 1, and what we left is 2 minus 1 over L or 2 minus R divided by B.
And you see in this case that was 1/10, so that's let's convince ourselves, so that's 2 minus R over B. Let's convince ourselves that this is really the best. So if that is bigger, by increasing L, R and B are fixed. By increasing L, we're making this worse. So what's the best possible choice of L? How small is possible in case 2? Yes? Right. Let's see what happens in case 1. When you look at that, 1 plus B divided by L times R minus 1 over L. That is B minus R 1 plus B minus R times this. That is just an R. How should you choose your L? Yes?
As big as possible.
As big as possible, because then this becomes smaller. Well, and that is, of course, again, so that is really what we should be doing. And then we get this as an answer. Now, final remark, it's basically a 2 and a slight correction factor. 2 is sort of intuitively fine. 2, you get a 2 by saying I pay as much in rent as it costs me to buy, and then I buy. That covers you for this period of rental, and then at some point you say, okay, now it's worth, that's what I spent. I'm sort of protecting against this one case, and then I'm buying. So you have two different choices, and you combine these two strategies, basically. Now there is this little correction factor here, and this correction factor, you could argue, is a bit of an artifact, because it comes from the fact that you're making the decision on the morning when you know that you will be skiing, so you are safe. If you have to make that decision slightly in a different way, if we did our bookkeeping in a different way, when you are making that decision, making the decision to rent, then you know you get the day. But if you make the decision like the evening after, and then you break a leg in après-ski, then you don't even get the use of that, right? That shifts the whole thing. So in that case, you can think about that. In that case, you get a clean even too. So this correction factor is if you want a consequence of that you are sure that you can use it when you do rent it. If you change the scenario and you say like, you're stepping out of the rental shop and then you break the leg, then the whole thing shifts a little bit and then you get a clean too. You can look at that and think about that. That was the first lecture. That was the first problem. Of course, you see, this looks a little artificially complicated. It's a simple problem. Now, doing this general and with these numbers and so on, go back and look at these. It's not so super complicated here. I would encourage you to look at this again and check the numbers and all these sorts of things. But the idea is very simple. The idea is you have these two solutions, the rental solution, the buy solution. You have these two together. That's 2 for 1. That's a factor of 2. And the rest is, just busy work with shifting around some terms. That's it for today. Thank you all. We will stop the camera now in a moment. And feel free to send emails. Feel free to ask me more questions. But I will see you all not next week. Because next week I will be trying to deal with water. We have a project on climate change and extreme water events, and I'll be in Bonn about some of these things. So no lecture next week, but we'll meet again the week after. Thank you.
Thank you.